Hello, Life Science class. This is your notes for the 18C section. We're going to talk about ionic bonds here. One thing I want to point out is typically metal and non-metal are going to be bonded together when we find ionic bonds. So just a little bit as opposed to the last ones, the covalent bonds, which tend to be between non-metals only. Okay, I want to look here at the top slide here. When we talk about ionic bonds and we talk about a metal with a non-metal, what I want you to think about is visualize the periodic table and see on the right side of the periodic table you have the non-metals. On the left side of the periodic table you tend to have the metals, right? So what we're going to see here is elements with very different electronegativities, right? You have something that has a lot of valence electrons on the non-metal side, something with very few valence electrons over here that are metals on the other side, right? So very different electronegativities. An electron appears to have transferred electrons from one atom to another. That's going to affect the bond. Generally, like we said, we're going to see metals and non-metals, right? No purely ionic bonds. Okay, I want to look at the concept of ionic bonds and what we would see as a limitation for using our electron dot notation. Remember, electron dot notation is like an element that is going to have our valence electrons shown around the outside, right? Like we would have sodium binding together with chlorine. Well, we would draw the electron dots around the outside, showing that sodium has only one valence electron, and chlorine has 7, right? It's in the halogen family. So we would draw our two separate electron dot notations like that. What we see, though, is we get the idea that this is a really fast process. But what we need to know is it happens in steps, okay? It does not typically happen all at once. I don't know how else to use an example of this, but if you are wanting to date somebody, it's not right for you to date two people at the same time, right? That's kind of mean and nasty. You got to break up with one person before you can date another, right? So I want you to think about bonding like that. This is an example of fluorine and sodium, right? Sodium has Na, has 7, or has only one valence electron. Fluorine, on the other hand, group 7A, has 7 valence electrons. So fluorine only has a need for one more valence electron, and it will have its perfect 8. So logistically, it's going to be easier for fluorine to take one valence electron from something else and bring it into its orbit so that it will have its full 8. And sodium, it helps sodium too, because sodium has this one lonely valence electron out here, and it wants to find a playmate for it, right? So it's going to pass it on over here to fluorine. And so we could draw our situation in those ways, right? Notice here what they're showing us, and I don't know if I can focus in a little bit more so you can see it, but it's kind of sketchy there. There we go. That's better. So what it's showing us here is sodium is going to go over and give its valence electron to fluorine. that's going to make sodium have one less. I don't know if you can see it, but if it has one less electron, that makes sodium a +1. So that's what that says. Fluorine, on the other hand, is going to be neutral, but if it takes on one extra electron, that means now it's going to have one extra negative charge. So you're going to have this idea that something that's positive is going to be attracted to something that's negative. It's a natural law, right? We talked about that in electricity. Positive and negative attract. Same thing with magnesium and sulfur. Only thing that's different here is when we think of fluorine or we think of sulfur, they have differing numbers of valence electrons, right? Sulfur is in group 6A, so it has 6 valence electrons, whereas fluorine is in group 7A, so it's got 7 valence electrons. That's going to be a little bit different, right? Magnesium is in group 2A, so it's got 2 valence electrons it wants to give away to some other element. This magnesium is also going to have 2, right? So I want you to think about this logistically. 6 plus 2 equals 8, right? So this 2 valence electrons being given to this 6 is going to be a natural, easy transition to get 8 valence electrons total. Magnesium bonding with fluorine is going to be a little bit different because 7 plus 2 does not equal 8. Okay? In order for this to happen, if magnesium is finding something, right? Here we are with magnesium, it's got its 2 valence electrons. It's going to give its 2 valence electrons away to separate fluorines. And that's going to make the process here a little bit different than the process up here, right? Magnesium plus 1 sulfur takes care of all of the connection issues, but magnesium with fluorine is not going to happen. It doesn't work. 2 plus 7 does not equal 8, so we've got to make adjustment, and magnesium is going to have to find 2 separate fluorines for it to give electrons away to. Sodium and sulfur. Sodium having it's in group 1A, so it's got 1 valence electron, right? And it's binding together with sulfur. Well, sulfur comes from group 6A. 1 plus 6 does not equal 8, right? So what we've got to do then is figure out, how is that going to be possible? So in this case, sulfur is going to need to take 1 valence electron from 2 separate sodiums, right? One sodium has 1, another sodium has 1. So they're each going to give a valence electron, and so we're going to have a threesome here, right? 2 sodiums and 1 sulfur. What we're going to look at here, just a couple more notes and we'll be done. The ionic compounds are going to tend to form crystal lattice, right? When you think of an ionic compound, I want you to picture sodium chloride. That's table salt, right? Sodium is our metal, chlorine is our non-metal, right? They're going to share electron, or not share. One is going to give, the other's going to take. They're going to form an ionic bond between each other, so they become an ionic compound, and there you have a crystal lattice. When you think crystal and you see lattice, think very structured, right? Look at table salt. Each of those little teeny tiny cubes, very distinct shape and structure there. Okay, Forming crystals when they solidify slowly. What we're going to see here is sometimes crystals are going to happen very quickly and sometimes they're going to happen very slowly. When they solidify slowly, that's going to tend to have high melting points. It's going to take very hot temperatures to dissolve them. Many are going to dissolve in water. Water is an excellent conductor of electricity. Okay, that's the end of our section on ionic bonds. We'll look at metallic bonds tomorrow.